Hello everyone, my name is Josip, I'm Head of Solutions at Memgraph, and today I'm going to show you one of our industry demos on energy management systems and how you can analyze your data with it in Memgraph. So let's get started. Here I have my Memgraph Lab. Let's start our Memgraph MAGE instance, Docker image, and then Memgraph Lab is going to say to us to connect, and we are connected in Memgraph Lab. This is the overview tab where we have actually the front page of Memgraph Lab, and the tab that we want to check out is datasets, where we have actually our energy management system, so we can see what we can do with it. After loading our dataset, we can see that dataset is successfully loaded. We have 8,000 nodes, around 11,000 relationships, 4 indices, and yeah, we have the memory used in our RAM, because Memgraph is an in-memory database, so everything from the data is actually stored in RAM. If we check the tab from Graph Schema, we can see that we have a pretty simple graph. We have one generator which is connected to another generator, so we can actually do and go in the query collections tab, which is kind of like our library of query groups, which we can show to our colleagues, peers, and actually see through a story what's happening with the data set. So if we here actually match all the nodes, we can see that we are actually querying here the data set which covers all the generators which are connected in Europe. I'll explain the colors later. The colors are actually associated with our graph styling and an algorithm we use there. But yeah, as you can see, we have different groups. We have generators which are really densely connected, but we can see that even these generators are somehow grouped together with a color. Like I said, I'm going to later explain what those mean, but at first glance you might not actually see what you want to query, but actually when we're talking about connectivity in power and connectivities of generators, one might ask ourselves, like, how well connected are these generators? Like, what if a group is not well connected? Will there be a power outage? Or if we remove one edge, such as maybe these ones here, what will happen to the nodes at this part of the graph? Will they be out of power, or will there be something else? Do we need to do alerts? Do we need to do impact analysis, risk analysis, and stuff like that? So we can see based on the queries what we can actually extract from this data set. Memgraph is specifically and particularly well in traversing, and it has actually added to Cypher syntax its own path filtering syntax. As we can see, this is a query which matches a path from this generator with this ID right here to this generator right here, using the weighted shortest path, or as it's commonly known, Dijkstra. Here is also written the cost function, which is equal to 1, and that means that we're actually using the same algorithm as BFS. So if we actually run the query right here, it can actually yield us pretty fast shortest path between two generators, one in Portugal and the other one in Russia. If we look at the documentation which I have prepared on the other screen, we have actually built-in graph algorithms. We have 4 of them: DFS, BFS, weighted shortest path, and all shortest path. And we have different syntax-like embedded features that you can query on the database, such as like querying what relationships or multiple relationships you want to querying by number of by the depth for every path, querying also having like a inline path, inline filtering of nodes, relationships, and even a filtering of paths that you are currently traversing, which all actually bring the sense that you need to query and retrieve the most accurate results, so you don't need to worry about any pre-processing, any post-processing. Actually, all the traverse is done in Memgraph, and you get exactly the results you want. So it's a very powerful tool. We are always expanding on this feature because we think we have a strength in it, especially because we're in memory, so we're very fast and we can do these traversals pretty quickly. So the next algorithm is called get bridges. So bridges is a concept where if you actually detach a part of an edge, that node or a group of nodes will actually become detached from the graph. So let's see what bridges actually yield us, and bridges has yielded us these edges. So let's say if I cut this edge out of the graph, then two nodes will become disconnected from the rest of the graph. Why is this helpful? Well, in the bridges algorithm, you might ask ourselves, okay, like what are some of the components which are not well connected, and if they are not well connected, what's then the impact? And the bridges might actually yield us some decisions in which we would want to strengthen these connections in the graph and make sure we don't have a single point of failure in our bridges. Next algorithm is called observe weakly connected components. Weakly connected components is called with this module right here is called weakly connected components.get, and I'll just go into a quick digression here and into this cipher syntax, and it's called call a procedure or something like that. This is actually called a query module, and is a piece of code which is written in Python or Rust or C++ or everything, and it's a piece of code that executes in the transaction and yields the results via the API back to the query. So this whole query is actually a part of one transaction, even though this is executed in Memgraph, and this is also actually executed in Memgraph, but using the Python interpreter or using the runtime for C++. So actually this is a very powerful tool because it allows you to do graph algorithms on top of graph storage, and everything is actually executed in Memgraph. So if we actually see the slide, which is let me find it here, we actually start the transaction as a pure cipher query, then we actually execute the code inside. The code actually gets us the results back into the query, and then we finally go and finish our query back. What's done actually in some of the other databases, like they might do a query, then do a first transaction, process it in the application, get results, then write back to the database. It makes the whole round tripping the bottleneck, and it doesn't make sense because you want to make your actions as one unit of work. You want to execute it in the database, and that's actually basically what we do with this. So let's get back to the actually weakly connected components. This actually command prints us the number of components in the graph which are disjoint. We here have 2 components in the graph, and if we observe the weakly connected components, if we query by the component ID, which we have set in this query previously, we can actually see the region which is actually disconnected from the rest of the graph. So why is this helpful? We can maybe set alerts if a component is detached from the graph and see, okay, your graph is detached, maybe someone will have a power outage or something. Maybe you need to do some actions in order to not prevent, but actually cure the situation because it's already happened. Or you might say, okay, what if I cut this edge out? Will I have detached components, and what do I need to do next? Next algorithm is the community detection, which actually sets us what components are actually very well connected. And I have actually run already this algorithm, so let's just go through this query which prints us the communities. And the communities, we can see we have a lot of them, and like more than 100 nodes, more or less, are in every of the component. And if we then get back to our first query, this is actually what we get with community detection. We have all the groups colored, and we can observe that some of the countries are actually really well connected, while the borders of the countries are not well connected. That's where actually the other group starts to be present in the community detection. So we can actually see here like traces of Turkey. This is Italy, this is Spain and Portugal, and this is Africa and United Kingdom, Ireland. Yeah, we can see that community detection really well connects these places, because you would expect that in the borders it would be a little bit lower connectivity than in a country. So actually, with the graph style editor, which is similar to CSS, it's developed in-house in Memgraph Lab, we can see that if a node has property of a community ID, then we can do some randomization of a color, and we can actually see very well what are the groups that are connected. So yeah, now you might ask ourselves, okay, but cross-border edges are not well connected. That's not a problem for us, because like that's how it should be. We probably countries have well connected pipes between generators between the countries, although they have less edges, or less actually pipes that are coming through the countries. But we might actually want to analyze inside the country what's happening. And now when we have our community IDs assigned to the graph, we might want to analyze actually a subgraph. And actually, if we analyze all the paths from the generator with community ID to all the paths with community ID using the BFS, we will actually get our graph, which is a subgraph in the Italy region. And yeah, as we can see, we have now gotten a subgraph. And what's then fun about it, we can actually go and write this subgraph on its own. On the next query, we have calculating maximum flow between Milan and Venice. And to get a subgraph, what you do is actually use the project function and analyze the subgraph. And then with this graph, we can actually query the query modules on the subgraph. You query a query module on the subgraph just by putting the graph in front. If nothing is in front, if a query was written like this, then it would be executed on the whole graph. But this way actually it's executed on a projection. So actually, if we go and do the projection and do the max flow algorithm, we'll get the results, and max flow is actually 11 units, whatever that might seem. I haven't actually showed you what's inside the nodes. So actually it's community ID, component ID, flow ID, latitude, longitude, and betweenness centrality, which is also an algorithm. These whole algorithms are not written by me personally. We have an open source library of graph algorithms. It's called MAGE. Let me just go through it real quick. MAGE docs. And there we have actually advanced algorithms, available algorithms. You have all the things you might want. Here is our community detection algorithm. You have the usage. You have what's the inputs, what's the outputs, what it does basically. And yeah, looking at it really quick. Here is our brochure of the available algorithms. Here we also included the built-in cipher, although it's not actually the part of the algorithms. But yeah, so stuff like page rank, stuff like community detection, stuff like betweenness centrality, bridges, cycles, max flow are all here. So let's go back to our data set and see what else can we get with this graph. We can see how maximum flow travels from one way to another. If we go, we can actually see Milan to Venice. Okay, this is the maximum flow that travels on these paths and is colored like this. Next one, MAGE library has the Betweeness Centrality, and actually it calculates what's the Betweeness Centrality of every node. Betweeness centrality is the measure of centrality of a node based on how much it stands on all the paths between pairs of all nodes. So actually, if you actually cut some edges, which might have been another path, which didn't go through that node, now that node is more important because it's the only one that stands on the path between groups of nodes, between pairs of nodes actually. So actually we can see the score of the node close to border of the UK and France. Let's see, it's Betweeness Centrality, and I'm not sure even which one it is, but it's actually 0.089, and it might be somewhere right here. So yeah, these nodes are on the path between UK and everything else that happens here in the Europe. So actually, if you actually cut one of these edges here, then it might happen that these nodes actually get bigger centrality because now more paths actually come through these nodes. So if we had a trigger which will actually call Betweeness Centrality based on the updates of based on the updates of the graph, we'll actually run again our Betweeness Centrality, and we can see here actually if we delete some of the edges, then our Betweeness Centrality will run again, and we can check what's the score inside the same. So actually this one before node was so we see 5060 ID, Betweeness Centrality was 89. If we query that again, we'll get different Betweeness Centrality. It says 0.101, which means our online Betweeness Centrality has actually calculated the value. How is this generated so quickly? It's because it's called Betweeness Centrality Online, and it's a concept of a dynamic algorithm. So what a dynamic algorithm is actually it doesn't recompute all the values from nodes from the whole graph, but it's actually just computing it on a local change that happened. And which local change happened, which it happened that we deleted these few relationships, and based on that we updated the local values for a fraction of the accuracy. We got actually real-time execution of a graph algorithm such as Betweeness Centrality, and we are able to stay up to date with our data set. So yeah, we actually come to the end of our data set. I hope you like this presentation about what can Memgraph do in energy management systems. I hope you'll gain new ideas about what you can do to, I don't know, even to check connectivity in your graph, to check supply and demand in your graph, to balance things in your graph, to do traversals, to do algorithms, yield new things for your business, and yeah, hope you gained some knowledge from it, and that you'll keep using Memgraph as your go-to graph solution. Thank you all, and see ya.